I suppose most of you have seen a crystal at one time or another, probably in a natural history museum or in a chemical bottle. Here's an unusually big crystal, dug out of a clay pit in Brazil. Here's a smaller one, broken from the side of a cleft in the rock in Arkansas. But crystals aren't always big, beautiful things like this. As a matter of fact, crystals are everywhere. The salt you use to flavor your food, for example, it consists of little crystals of sodium chloride. You can see their shapes by looking at them through a magnifying glass. Little cubical crystals of sodium chloride. Snow. Here are some enlarged pictures of single snowflakes. Each is a single crystal of water. Here's a crystal I like especially well, probably because I made it myself. It's a crystal of alum. As a matter of fact, you can make a crystal just like it. I put some directions in the film notes in case you want to do it yourself. You buy the alum you need at a drugstore and grow the crystal in a mason jar. If you do this, I'm sure you'll be very much impressed by one thing. The crystal keeps growing, maybe for a week. It keeps getting bigger, but all the time, it has plane faces, meeting in sharp edges. You can see I haven't ground the faces on this crystal or polished them at all. This is just the way the beast grows. It almost seems as if you were getting something out of nothing. Something with a shape all its own, which it decides all by itself throughout its career. In order to grow a single perfect crystal as big as this, you have to take pains and let everything happen slowly. But you can see what's actually happening by letting things happen a little bit faster and looking at the business under the microscope. I'm going to take a solution of alum, which is just itching to deposit crystals, and make a little pool of it on the microscope slide, and then add a few little crystals of alum to give the alum something to deposit on. And then get myself in focus and let her rip. There they are. You can actually see them grow if I turn now to a higher magnification. The little crystals keep pretty much the same shape as they grow, just getting bigger. Naturally, they all sit down on the microscope slide on one of their biggest faces. So you see the shape of the crystal depends mostly on what the crystal is made of, and not on its size, so long as it's free to grow in all directions. Now, crystals don't only grow out of solutions. They grow out of gases. Snowflakes, water crystals grow that way. And one of the most important places where crystals grow is out of melted materials when you cool them. Here I've got another powder you can get at the drugstore called Salol, which melts to convenient temperature. I'll put a little of it on a microscope slide. Then I'll carry it over here to the hot plate and melt it. And now let's go over here to the microscopes. There's one growing, turning very slowly in the liquid as it grows, because it hasn't quite sat down on the slide yet. It seems almost to push those flat faces ahead through the part that's still melted. Of course, you know that the whole crystal isn't moving and shoving its front along. The liquid next to the face is becoming solid and adding itself to the face. But it's doing this in such a way that the stuff added on also forms a flat face, so the crystal keeps its shape while it grows. Now, I'll melt this back carefully on the hot plate so as to leave just a little rounded blob of crystal. That rounded blob will be a single crystal, but it won't have flat faces. And I want you to see what happens when this cools down again under the microscope. There it goes, growing the faces it wants to have, filling in the hollows and squaring off the rounded corners so that its boundaries are all flat again. Notice now what happens when two crystals bump into each other, so to speak. They don't push each other around. They just stop growing where they meet because they've used up all the stuff to grow with there. So the boundary between two crystals isn't necessarily one of the natural faces on either of them. The boundary line just depends on how the crystals happen to come together. When the whole thing is finally frozen, you have a dense mass of crystals. Maybe no single one of them shows any of its natural faces, but the whole mass is made up of crystals just the same. Almost all rocks are made up this way. Granite's a good example. Here's a hunk of it. Let's take a close look at it. You can see grains of the different colored minerals which make up granite. Here's a grayish grain of quartz. Here's a grain of pink feldspar. And the little black flecks are grains of a kind of mica. And each of these grains will be a single crystal. Notice that the three things don't mix together in the solid. They crystallize out in separate grains. Before I get through, you'll begin to see why. When you came in, I was melting some bismuth in a crucible over here, and it's been cooling. And crystals ought to have formed on the sides of the crucible so that when I pour off the part of the bismuth that's still melted, you can see them. Sometimes you can show up the crystals in a finished piece of metal by polishing the surface and then etching it carefully with something that will eat away the metal. Here's a cast brass door handle, which the manufacturer polished, and then over the years, the sweat on people's hands etched it, and now you can see the boundaries between some of the crystals which make up that door handle. In most pieces of metal, the crystals are much smaller than these crystals because they've been broken up when the metal was drawn or rolled or hammered into shape. But the metal is crystalline just the same. Well, so almost all solid things are made of crystals. In fact, if you ask a physicist these days to define a solid, he'll probably say a solid is a bit of matter that is crystalline. Of course, that doesn't seem to get him very far because somebody is sure to ask, what do you mean by crystalline? But he's got an answer to that one. The answer comes in two parts. The first part says all matter is made of atoms. The second part says in crystalline matter, the atoms are arranged in regular order. I want to talk a little more about what he means by this and show you a little of the evidence for it. The idea is that the crystal is a pattern of atoms, a regularly repeated pattern of atoms, like the regularly repeated pattern of a wallpaper. If the atoms were flat and made a two-dimensional crystal, they might be taking up an orderly arrangement, like this arrangement of pennies on the table. In 3 dimensions, they might be making an arrangement like these bearing balls, closely packed together. Of course, these close-packed arrangements aren't the only arrangements the atoms might take. They're just simple examples of what I mean. Now, already, perhaps, you can see what these two ideas, the idea that a crystal is made of little units, atoms or molecules, all alike, and that those little units are arranged in the crystal in a regular array, you can see how those two ideas would explain what you've been looking at under the microscope. For instance, those alum crystals kept a symmetrical shape as they grew. Now suppose you had a two-dimensional crystal, like with a pattern of atoms like the arrangement of pennies. There are more atoms in solution all around it. But since the arrangement is symmetrical in the crystal, you expect pennies to add themselves on at the same rate here, and here, and here, and so on, because conditions are the same at all those places. The crystal will grow symmetrically and keep its shape, so long as nothing gets in the way and prevents more atoms from reaching the surfaces. Let me show you another kind of evidence for these two ideas. It's a kind of evidence which doesn't come from the process of growth. It comes from the properties of the finished crystal. This is the evidence of cleavage. If you've ever handled mica, you're acquainted with cleavage. The mica crystals you find in nature come apart easily in one direction and not in any other, so that you can split them into extremely thin, tough sheets. The mica acts as if it was made like a book, with a lot of leaves of tough paper. But if you actually try it, you'll get the feeling that there's no limit to the thinness of those leaves of paper. You'll feel that if you were skillful enough, you could split each leaf of the mica in two, and then each of those in two again, and so on. It makes you guess that the atoms in the mica are arranged in great sheets, that the atoms are bonded together very tightly in the sheets, and the bonding forces between the sheets are very small. Just the arrangement of atoms in sheets like that is a kind of orderliness. There aren't many crystals that cleave as well as mica. Alum, for example, doesn't cleave at all. But a great many crystals do cleave amazingly well. Let me show you the cleavage in this crystal. It's a crystal of nickel sulfate hexahydrate. It cleaves parallel to this face. I'll put the thing down on a little plasticine to hold it in place. I'll take a single-edged razor blade and direct the blade parallel to the face and give the back of the blade a smart tap. She comes apart. And now look at that, as flat as you please. You may say, oh, you picked a special place in the crystal. But look, I can cleave it again, parallel to that same face, and get a thin plate out of the thing. So it isn't a special place in the crystal, it's a special direction in the crystal. Now maybe you'll say, oh, that isn't any special direction. You've got a sharp razor blade and you're cutting the thing apart with it. All right, if that's what you think, let me try the same stunt in a different direction. I turn my razor blade in a different direction, and I whack it, and nothing much happens until I whack it a lot harder. And finally, of course, the thing busts. And there's no nice flat face. It's just broken apart like anything else. Now let me show you the cleavage in another crystal, a crystal of sodium nitrate. Here's a crystal that cleaves in three directions, not just one. I can cleave it here, like this, and I can cleave it here, like this, and here, like this. By the way, you can grow both these crystals, nickel sulfate and sodium nitrate, by recipes given in the film notes in case you want to play around with the stuff yourself. Sodium nitrate has a lot of interesting properties. It has most of the properties of the mineral calcite. When big crystals of calcite were first discovered about 300 years ago in a quarry in Iceland, the scientists of that day got hold of some, and their studies of the stuff made the first big start in our understanding of crystals. As I say, sodium nitrate and calcite have many properties in common. In particular, they both cleave the same way. When those earlier scientists saw the way calcite cleaves, they had the idea that maybe calcite was made of tiny building blocks, all alike and all having the shape of little cleavage blocks of calcite. You may be inclined to laugh at this and say that calcite, like all matter, must be made of atoms, and atoms don't look like building blocks. Okay, you're telling me. What do the atoms look like? Little hard round iron pellets? Don't let me fool you with those pennies and bearing balls I've been showing you. They just show where the atoms are, not what the atoms look like. For all I know, the atoms look like four-leaf clovers. I want to emphasize that those early scientists produced both of the main ideas which go into the picture of a crystal that we have today. First, they were saying crystals have an ultimate fine structure, the building blocks. We would call them small groups of atoms instead of blocks, but the difference is really more a matter of words than of anything else. Second, they were saying That structure has a regular array. The blocks are stacked up in a regular order, and they keep stacking up in regular arrangement as the crystal grows. It turns out that you can think of any crystal, not only crystals which show cleavage, but any crystal, as made of little blocks stacked up in regular array without overlapping on top of one another and side by side, if you choose the right shape of block. In the case of alum, the right shape of block is a cube. And you can think of the alum crystal as made of little cubes, all stacked up on top of one another without overlapping this way. Notice that I've made the main faces on the model of the alum crystal by stepping back the cubes as I piled them up. At first, you might think that would mean that the face would be pretty rough. But you've got to remember that these little cubes are really only a few atoms wide. Their sides are only about 1/10,000,000th of a centimeter long, and you wouldn't feel that roughness or even see it under the microscope. One of the things that gave early support to the building block idea was the fact that all crystals of the same stuff have the same angles between corresponding faces. The crystals might be very different in size. They might have grown at different rates on different faces so that they have different overall shapes, like these two alum crystals. Nevertheless, the angles between corresponding faces of all crystals are the same, so long as the crystals are made of the same material. It all suggests very strongly that each material forms its own building block, which gets repeated again and again as the crystal grows. Now, turn back for a moment to the microscope and remind yourself of what is happening while a crystal grows. Atoms are constantly arriving at the surfaces and adding themselves onto those surfaces in an orderly way, and they're doing this at an amazing rate of speed. The crystals you're looking at are growing fairly fast. Suppose a crystal grew at the rate of only a couple of millimeters a day, which is fairly slow. You can calculate that about 1,000 layers of molecules would have to be laid down per second on the surface of that crystal. And all the molecules have to be laid down in the right sort of order. I want to borrow a trick from Sir Lawrence Bragg to give you just a rough idea of some of the things that we think must go on as a crystal grows. Sir Lawrence blows soap bubbles. He blows them in a pan of soapy water, tiny bubbles which rise to the surface and collect in rafts. The bubbles behave a little like atoms because when they're floating on the water, they attract one another a little. And when they touch, they stick to one another quite strongly, as atoms do. But, again, like the atoms, they have a squashy sort of size so that they take up space. Watch how the bubbles collect together into an orderly arrangement. It's the same as the arrangement of pennies I showed you, the so-called close-packed arrangement. Notice that the rafts are made of large parts. All of the parts have the same sort of order, but the orderliness of the parts is turned in different directions so that there are grain boundaries between the parts. This is like a solid made of lots of crystals which started growing in different places and finally joined. It's like the salal after it is all solidified, or that brass door handle. When you think of how fast the atoms have to get into order, much faster than this, the more astounding their achievement seems to be. But this will give you some little idea of what a hustle and bustle must really have to go on an atomic scale. Sometimes when the molecules are very big and have an irregular shape, they're too sluggish to get themselves arranged into order. Then they congeal into a glass. A glass is very much like a liquid, but it's like a liquid in which the molecules are no longer able to move past each other. It has patches of order in the midst of disorder. The disorder is frozen in place, so to speak, and can't get itself rearranged into order. Liquids and glasses are pretty disorderly arrangements of molecules, and gases are the most disorderly arrangements of all. The only order in gases is the arrangement of atoms grouped in each molecule of the gas. Later in this course, you'll learn more about gases. But already, you can see why gases are so very much alike in a great many ways, whereas there are so many different kinds of solids. The only way gases can differ is in the kinds of molecules they are made of. But solids can differ also in the kind of orderliness which those molecules take up in the crystals which comprise the solid. I can show you this selectiveness actually happening in some of the materials you've already looked at. I'll melt some salal on the hot plate over here. There. And bring it over to the microscope and let it cool down so that it wants to crystallize. Then I'll seed the salal with a tiny crystal of alum. Nothing happens. No salal will crystallize on it. Now, I'll seed the melt with a few little crystals of salal. And you can see the salal crystals grow, leaving the alum crystal unaffected. The orderliness of alum is not the right kind of orderliness for salal, and the salal simply waits until the right kind of orderliness is presented to it. And I think now you can see what I promised you would see about granite. Why it is that the three different ingredients, quartz, feldspar, and mica, form three separate kinds of crystals in the granite and don't form just a single crystal in which the molecules of quartz, feldspar, and mica all take part together. It's because those three kinds of molecules normally form crystals with three different kinds of order. When the three kinds of molecules are all together, they can't find a kind of order which is common to all three of them. So they crystallize out separately, each in its preferred way. You know, after 20 years of growing crystals, I still find the whole business nearly miraculous. You go to the microscope to watch it, and it happens again. And you know that the atoms are at work, busily, almost unerringly, constructing something. Something regular, something orderly, constructing something which, from an atom's point of view, is simply enormous.
Bill Plummer and I have just been demonstrating a phenomenon first discovered by Heinrich Hertz in 1886. It's concerned with the effect of radiation on an electrical discharge. We have been getting our radiation from a carbon arc. This concave first surface mirror detected some of that radiation and focused it on this magnesium plate connected to the negative electrode of a high potential source, and we have aluminum ball connected to the positive electrode. And we've adjusted the source very carefully so that when we have the plate in the beam that's shining on the magnesium, we just don't get a spark. But you notice when we take the plate out, then we get a spark. Some radiation that wouldn't go through the plate hit the magnesium electrode when we took the plate out, and that was the thing that caused the spark to flow. This was a precursor discovery made by Hertz, which led to a great many experiments of great importance, and we are going to repeat some of those for you this afternoon. use this natural light instead of the carbon arc we had inside, and we could use this simple electroscope instead of all that elaborate equipment that we had inside. Bill has put a glass plate on the front of it to protect the needle from the wind, and he's wrapped the glass plate with wires to shield the needle from any electric charge that might be on the plate. The wires are connected to the can of the electroscope. And now, will you put a negative charge on the electroscope with that plastic rod that gives a negative charge when it's rubbed? Here is a piece of lead foil, and if you'd hand me some of the steel wool, I'll get it clean. We'll put it on the electroscope, and of course when I touch the electroscope that discharges it. If you give me the piece of glass and charge it negatively, I'll hold this glass in front of the lead, and there we have a charge. Now I remove the glass, and we see that the electroscope isn't discharging. Now I'll try magnesium. This has to have its oxide removed too, and I'll bend it and put it on here. And now if you charge that negatively, we'll see that it isn't discharging with the glass in place, but if we take the glass away and let the sun fall on it, discharges, put the glass back, we slow the discharge up and take it away, and it discharges much more rapidly. Let's do the experiment once more, this time with the electroscope charged positively with a different plastic that gives a charge when it's rubbed. And now when I take the glass out, the electroscope doesn't discharge with the magnesium plate on it as it did before. We have just seen that the photoelectric effect depends upon the sign of the charge and the kind of metal on which the light falls. When the light from a carbon arc lamp is concentrated by means of a concave mirror on a magnesium plate, as before, we can get a similar effect. And furthermore, we can spread out the spectrum of the carbon arc lamp with a diffraction grating and find out what part of the spectrum is causing that effect. We have arranged our grating and our arc with a card so that we can see what part of the spectrum is shining on the magnesium. And as we move the spectrum across this card, you will see that the part that causes the electroscope to discharge lies beyond the violet end of the spectrum. This is the ultraviolet region. Magnesium responds to ultraviolet light by emitting negative charges. Other metals emit them for certain visible light frequencies and all radiation of high enough frequency, like soft X-rays. Because of the color sensitivity of this film, the ultraviolet striking the magnesium appears visible to you here, like violet. But as you can see, the glass that we used before blocks off just enough of the ultraviolet to keep it from discharging the electroscope. By shining our spectrum on this card and by using a more complete ultraviolet filter, you can see better how the ultraviolet is blocked out by the glass. At the top of the card, on the left, the ultraviolet causes a phosphorescent paint to glow. It also shows up as violet on the uncoated side of the card because of the film's color sensitivity. If we put the filter in the path of the light, the ultraviolet is blocked out. You can see these parts of the card go black. Remove the filter and the ultraviolet gets through. We cannot see ultraviolet radiation with the naked eye, but this is one way we can demonstrate that the radiation is present in this part of the spectrum. We're going to do a more precise experiment now. We're going to do an experiment with a different metal. We're going to use potassium instead of magnesium, and we're going to do the experiment in a vacuum. By doing the experiment in a vacuum, we can solve our cleaning problem because the potassium surface will stay clean in a vacuum. We can show that the effect which we observe is not just the ionization of the air near the metal surface, because in a vacuum we won't have any air. And finally, we can show that the charge phenomenon is the ejection of electrons, and particularly in a vacuum, we can show that we can measure the energy of the electrons that are emitted from the potassium when light falls on it. We have the potassium metal inside an evacuated glass envelope. Potassium not only shows a photoelectric effect for the ultraviolet that will penetrate this envelope, but for visible radiation as well. The ring of platinum wire serves to collect the electrons which the potassium may emit when it is illuminated. This cap is connected to the potassium surface by a wire, and the platinum ring, which you can see, is connected to the outside through an electrode opposite the cap. I will focus the light so it doesn't touch the platinum ring, but falls directly on the potassium through it. This will cause the potassium surface to emit electrons, and if I put an ammeter in the circuit, it will measure the number of electrons emitted by the potassium and collected by the platinum ring. Now we'll put our photocell in this light shield because we don't want to have any light falling on the photocell except the light which will come through this little hole. The platinum ring is connected to the top electrode, and we'll fasten this wire onto it, while the potassium surface, which is connected to the cap, is connected now to this wire. These two wires go to Bell's sensitive ammeter, which is located behind the light shield. We need light on the meters to read them, but we don't want that light to get into our photocell. Our light source for this experiment will be a mercury vapor lamp. We mount our mercury lamp in a shield to absorb all the light except the light we want to use, which comes out of this hole, and is collected by concave mirror, a concave front surface mirror, so that the light doesn't have to go through this glass. The collected light is focused through this filter, which we won't use in this experiment, so I'll take it out. Onto the aperture in the cell shield. And in order to make the shielding complete, I cover the platinum collector ring electrode, and of course I have to turn the light down. And now the mercury light is a little out of adjustment. The light is focused through this little hole, goes inside the platinum collecting ring and falls on the potassium surface. Now, let's see what current we get when we let the mercury light fall on the potassium surface. We have the potassium cell connected to a microammeter, and you can see the deflection of the needle as I turn the light off and on. This current measures the photoelectrons that are ejected from the potassium surface by the mercury light. And a full-scale deflection is 1/10 of a microampere. The whole significance of the phenomenon of the ejection of charge from metal surfaces when they're bombarded with light or with other electromagnetic radiation began to take form when the physicists began to measure the energy of the electrons that were ejected. And now the question is, how can we measure the energy of the ejected electrons? Well, this is easy. All we need to do is to put a retarding potential on the collector ring and vary the potential until the current through the microammeter just stops. And then the magnitude of that potential will measure the maximum energy of the electrons that are ejected by the light. I have modified this simple circuit by introducing a variable potential. I show that as a battery with an arrow through it to indicate that it's variable. To measure the potential, we have a voltmeter connected across it. You can see that I've connected the negative side of the battery to the collector ring so that I make it negative with respect to the potassium to retard the electrons. Here's the battery we're going to use. The negative lead goes to the collector wire. With a variable resistor that Bill can control by turning this knob, he can change the voltage, and he can read the potential exactly on this meter. Now let's measure this energy of the ejected electrons, and let's measure it for particular colors or frequencies. Our mercury vapor lamp emits several colors or frequencies. These are its characteristic spectrum lines, and we can isolate these, one color from the others, by means of filters, which we have collected here. Now let's start with this combination of filters. It will pass only the yellow light which comes from the mercury lamp. And we'll mount the filters in front of the aperture in our cell so that only the yellow light will strike the potassium surface. Because there's less light than before, we'll put the ammeter on a more sensitive scale, and you see when I interrupt the light with my hand, as before, the current drops to 0. Bill will now put a retarding potential on the collector ring. On the right, the voltmeter shows the amount of the retarding potential. You see that as we increase the negative potential, the current, read on the other meter, goes down to 0. To cut off the photocurrent required 0.25 volts of negative potential. Now let's watch both meters at once as we repeat that, increasing the voltage on the right until the current on the left hits 0. The retarding potential, again, was just 0.25 volts. Let's keep track of these results. The retarding potentials are plotted along the y-axis. Bill will keep track of this 0.25 volts by plotting it. Now let's try a filter which lets green light fall on the photosurface. Bill gets the retarding voltage necessary to stop the photocurrent as 0.35 volts. Now we'll try blue light. It takes a higher negative potential on the platinum ring to stop the photocurrent. In this case, Bill gets 1.05 volts. Now let's go to an even higher frequency in the mercury spectrum, into the violet. We get 1.3 volts as a cutoff potential. For the ultraviolet, we get an even higher retarding potential necessary to stop the photocurrent. Of 1.7 volts. Now Bill is going to connect these points and see what kind of a plot they make. Here the straight line tells us that the maximum energy of the electrons increase proportionally with the frequency of the light. Experiments similar to this have been done many times. In 1916, Robert Millikan published the results of his precise experiments using sodium and lithium. We have transferred his data to a graph so that we can lay it over our graph for potassium and compare it. We see that the retarding potentials needed to stop the current at any particular frequency are different, but the important thing is that each set of data gives a straight line and that the slope of each line proves to be the same. It is true that our straight line is off a little bit from the slope of the other two, but when you do experiments with the great degree of accuracy that Millikan used, then all slopes turn out to be the same. To understand the significance of these straight line results, let's go over the data. We plotted the frequency across the bottom and the energy of the emitted electrons measured by the retarding potential along here. And we got a straight line with a slope like this. The energy then of the emitted electrons for this frequency nu is just this much. The energy of the electrons emitted when the potassium was struck by light of another frequency, say here, was just this much. The amount of energy of these electrons is proportional to this frequency difference. nu minus nu zero. The amount of energy of these electrons is proportional to this frequency difference, this nu minus nu zero. And the proportionality between this energy and this frequency difference is just the same as the proportion between this energy and this other frequency difference. The factor which relates them is the slope of this straight line, and so we can express this relationship in the following way. The energy of electrons emitted at a given frequency is equal to the frequency difference, nu minus nu zero, times the slope of the line, which we express as h. This constant slope is now called Planck's constant. I'll rewrite that equation as E equals h nu minus h nu zero. Now you'll remember that for a different metal, Millikan got exactly the same slope, but that it intersected this line at a different point. Thus, there is a different nu zero for each metal, but because the slope is the same, this equation is true for all metals. This factor, h nu zero, then looks like it must be only a property of the metal. H is constant, but nu zero varies with the metal. It represents a property of the metal. This factor, h nu, must then be only a property of the light, and it is the same no matter what metal we use. This is an energy equation, so this must represent the energy of the light striking the metal. Light with this much energy, h nu, always causes the emission of electrons with this much energy, E. But the energy of the electrons that we measured with our retarding potential was the energy of individual electrons. We know this because the retarding potential is independent of the number of electrons flowing. I said we know this because we get the same cutoff potential regardless of the intensity of the light. You remember we used the mercury light with a blue filter, and we got 1.3 volts cutoff potential. Now Bill will measure the cutoff point for the blue light again, but this time he cuts down the intensity with a neutral filter. But he still gets 1.3 as a measure of the energy of the ejected electrons. We can cut off a large current at exactly the same point as a small current for any given frequency of the light. So this then is the energy of an individual event, the emission of an individual electron. Our experiments show that the electrons that are ejected from a metal surface by light, their energy does not depend on the intensity of the light, but it depends solely on the frequency of the light. And furthermore, when we plot the energy against the frequency, we find we can represent our results with a straight line. And although different straight lines are required for different metals, they have in common the same slope. And this universal slope is called Planck's constant. No other theory but the quantum theory satisfactorily explains this universal slope. And so we're constrained to think of light as traveling in packets. And the energy of each packet is determined solely by the frequency of the light. And we call these packets photons.
Alpha particle tracks in a cloud chamber. Traces revealing the passage of minute fragments of matter traveling at great speed. You recall these tracks mean that ionization is taking place due to the passage of a projectile carrying an unbalanced electric charge. For alpha particles, the electrical unbalance amounts to two positive elementary charges. Today, we are going to see how Ernest Rutherford used alpha particles to investigate the structure of the atom. Rutherford knew a good deal about the alpha particle. He had measured its mass. He had measured its electrical charge. As a matter of fact, he had determined that an alpha particle is a helium atom without its balancing negative charge. It's 2 electrons. He had measured the velocities of alpha particles ejected from radioactive elements, and it was after he had observed alpha particles passing right through gases, liquids, even metal foils, and knew how to count them, that he realized that he had at hand a tool with which to explore the inner structure of the atom. Let us look a little more closely at these atomic probes, these alpha particles. This time, we will use a cloud chamber of different design. Our radioactive source is polonium, and it is held in place by the screw on the left. Beyond the alpha particle tracks, you can see a small wire scale that we have laid on the bottom of the chamber, and against which we can judge how far the alpha particles travel. Notice that the longest tracks go out about 4 divisions on the scale. Now we can set up a barrier across the path of the alpha particles using a metal foil. This is gold foil, similar to that Rutherford and his assistants used. It is very, very thin, only a few thousand atoms thick, and it's hard to handle. Nevertheless, we've managed to get our cloud chamber fitted with its barrier. You see it here as a fuzzy light line across the face of the source. The alpha particles pass right through it. To look at the tracks, you'd think the gold foil was not there at all. The particles go through it with ease. But there is a little difference showing up. Distance. Now the longest tracks go out only about 3 divisions on our scale. They don't seem to travel as far. The foil has reduced their energy, slowed them down a little, and they are consistently stopping short of their former range. There is another effect that the gold foil has on the alpha particles that we cannot see just by examining these wispy tracks by eye. The tracks are ever so slightly deflected, rarely by more than 1 degree. Rutherford suggested a study of this deflection to his colleague, Hans Geiger, who was already on the way to perfecting the now famous Geiger counter. This is how Geiger proceeded. At one end of a glass tube, evacuated, and about 1.5 meters in length, he placed his radium source. Partway down the tube, he placed a slit to give him a narrow, well-defined beam of alpha particles. At the other end, he placed a scintillation screen. He used a microscope to see the flashes produced by the alpha particles as they hit the scintillator. When he used gold foil, he placed it over the slit. With this equipment, he recorded the distribution of alpha particles, with and without the gold foil, and prepared a graph of his findings. The center of the beam of alpha particles, 0 degrees. These figures represent the angles of deflection of the alpha particles in degrees, and of course the vertical coordinate represents the number counted. This is the beam as he saw it without any gold foil present. You can see that it is only 1 degree wide and had very sharp edges. This second graph shows the effect of the gold foil. The beam fuzzed out at the edges. About half the particles were deflected through 1 degree, a few to 3 degrees, but none beyond 5. The equipment for our demonstration is arranged a little differently. Our polonium source is on a rod here in a cylindrical brass tube. Here's the aperture through which the alpha particles emerge, and we have made our aperture quite large so that a great number of particles will pass through the gold foil in a short period of time. Where Geiger's beam was about 1 degree wide, ours is, in fact, about 70 degrees wide. The gold foil is here, and our electronic detector is here, and is movable in an arc about the gold foil. Since we are not using a vacuum, as Geiger did, our components must be grouped closely together. This is the tube containing our polonium source. Here's the thin gold foil. And here's the detector we will use to count the alpha particles that penetrate the foil. It's a brand new device made out of a transistor. It gives a sharp electrical impulse as an alpha particle hits it. Here, it is connected through an amplifier to an oscilloscope and a loudspeaker. This arm pivots, letting us move our detector in an arc across the beam of alpha particles and out of it on either side at any angle. Our detector is light sensitive, so we'll place a shield over it and read its angle by this marker. Now we'll switch on the amplifier and hear a snap from the loudspeaker for each alpha particle. We also see a pulse on the cathode ray tube. Even though we are working with a much broader beam of alpha particles than Geiger did, we can still see on our counting equipment the rapid fall-off at each edge of the beam. Here are the alpha particles, about 500,000 per second in the beam. The beam goes from here over to here, diminishing rapidly, and we'll mark this as the edge of the beam. In the same way on the other side. Here they diminish rapidly, and we'll mark this as the other edge of the beam. And now if we go beyond, we find none. Perfectly quiet. None of the alpha particles are deflected more than a few degrees from their original direction. What was that? A count? At this angle, that's 25 degrees out of the beam. There's another. That was 3. Is the gold foil really responsible for these counts? Let's see. Silence. Now let's put the gold foil back. Now the gold foil's back in the beam of alpha particles, and we'll wait and see. There's a count already, too. This wide-angle scattering seems to be caused by the presence of the gold foil, all right. What is going on? This is what Rutherford wondered when the discovery of these wide-angle scatterings was first made by Ernest Marsden, a young graduate student under his direction. Marsden found that on the average, about 1 alpha particle out of every 8,000 was deflected through more than 90 degrees. What was there about the structure of matter that would give rise to such violent changes of direction for a few alpha particles and scarcely any for the vast majority? Here is a model that will enable us to examine this problem more closely. These steel ball bearings will represent alpha particles. The ramp will launch them with uniform energy. This, of course, represents our gold foil. Now let's launch some. There goes one. These hot ball bearings leave tracks as they cross our specially prepared waxed paper. There's a fourth and a fifth, but this one was deflected through a large angle. Two more, straight. Another one, straight. Another straight. Another straight. And another one. We have set off 11 in all. Of the 11, 10 have followed the kind of course Geiger observed, but one has undergone a large deflection of the kind that Marsden observed. Let's run out about 200. Now we have our sensitized paper record about as full as we can make it. How did we make out? How many violent collisions? 1, 2, 3, 4, 5, 6. These points in our gold foil look suspicious. Let's see what's there. Aha, hard steel fins. No wonder the balls bounced. Our model gold foil is not really uniform in structure. It consisted partly of fuzzy felt space, through which our so-called alpha particles penetrated with ease, and partly of small, massive scattering centers. This sort of possibility is what Rutherford guessed at. He knew that atoms were full of electricity. Ionization, electrolysis, and so on suggested that atoms had lots of electricity in them, despite their being electrically neutral when undisturbed. And he knew the negatively charged electrons were very light compared to the mass of their atoms. So he proposed that all of the mass of the atom, except the little part belonging to the electrons, might be concentrated, really concentrated, in a minute space at the center of the atom, leaving the rest of the atom empty, except for the light electrons. Then, if this massive core were to carry a large electrical charge, the electrostatic force between this charged core and the charged alpha particle might explain the wide deflections. Now, if this view of the atom were true, how could it be checked? Rutherford turned to the very deflections that had created the puzzle. He would make an accurate record of the deflection angles, tell him what kind of collision had taken place. Can you tell from a series of collisions what force is responsible for the deflections? Do you remember the toy train cars? They made a collision at a distance because of the forces of repulsion between two magnets. For magnets not guided by tracks, a magnetic deflection looks like this. Or this. You can see the angle of incidence and the angle of emergence. Sometimes that's all you can see. But a study of the angles of deflection can often tell us a great deal about the nature of the force that produced the collision. Here's another collision you are familiar with. It is often called a hard sphere collision. Nothing happens until the spheres appear to come into contact. Now, this is a type of collision you may not have seen before. This is a very light, dry ice puck. It seems to be working all right. And this is a small Van de Graaff generator. Let's switch it on. When it's charged up, it has a large positive charge. Now let's share the positive charge on the Van de Graaff sphere with the sphere on the dry ice puck. When the two spheres are charged, they have the same type of charge, and they repel each other with a Coulomb force, a force which varies inversely with respect to the square of the separation of the two spheres. Now let's see an electrostatic collision. There was a wide encounter and a deflection angle of about 45 degrees. Now let's charge the sphere again. It gets hot to handle by hand. Let's try a more direct encounter. There it goes slowly in and deflected almost directly backwards. A deflection angle of about 150 degrees. Now let's charge it again. And see another encounter. Each of these encounters shows a deflection angle that's connected with the encounter distance in a way characteristic of the electrostatic force. Let's charge it again. That encounter produced about a 90-degree deflection. We have seen three types of collisions: magnetic, contact or hard sphere, and Coulomb or electrostatic, and the types of deflections each produced. As a matter of fact, any type of force at work in a collision produces its own characteristic deflections. Rutherford strongly suspected a Coulomb-type interaction, rather than magnetic or hard sphere or any other kind. So he set about calculating the deflection pattern that his positively charged, minute atomic core would produce. Using Coulomb's law, he deduced the angles through which the alpha particles would be deflected as a function of how directly they were aimed at the center of the atom. Square at the center, an alpha particle would turn through 180 degrees and come right straight back. If it approached a little off-center, as this one does, it would be deflected through a large angle, say 125 degrees, and come out here. Another one, approaching a little further off-center, as this does, will go through a lesser angle and come out here. Another one, approaching still further out, like this, would come out here. And another one, approaching way out here, would only be deflected by the Coulomb force through a small angle, say 45 degrees. Each of these trajectories and all the intervening paths Rutherford found to be hyperbole. And it isn't just in this plane that these trajectories occur. They occur all about the nucleus of the atom in this three-dimensional space. Here's a hemisphere that will help us picture the directions along which the alpha particles fly away from the nucleus after being deflected by the Coulomb force. And I will ask you to picture another hemisphere under the table, for everything that I say about angles on the upper hemisphere will apply equally well to the lower hemisphere. When Rutherford was satisfied that he understood how each individual alpha particle would behave under the influence of the 1 over r squared Coulomb force, he turned his attention to a calculation of the fraction of the alpha particles that would emerge at each angle. That is, how they are distributed as they come out. From this direction, we can imagine a uniformly distributed rain of alpha particles. An alpha particle that falls at this point on the rim of this smallest circle will follow a trajectory indicated by this wire, go in toward the center of the atom, and emerge along this direction. One striking the same circle at another point, say here, will go in toward the center and come out along this direction. In fact, particles striking anywhere on the rim of this circle will come out in directions like this through this arc. And I'll draw the arc. In a similar way, a particle entering the Coulomb field here, at this point, on the second circle, will go in along this trajectory and go out along here. In the same way, all around this circle. And I can draw an arc to represent the places where alpha particles with exactly those trajectories will emerge from the nucleus. And for this third circle, the particles will fly out at angles through this arc. Lastly, particles approaching somewhere out here will emerge through an arc along here. Now we have the spherical space about the nucleus of our atom, marked out with certain limiting arcs which are determined by the trajectories we established before. In fact, each of these circles is directly related to each of these arcs. For instance, all of the alpha particles approaching the nucleus within this inner circle will come out at angles greater than those approaching right at its rim. That is, they will come out through this cap zone here. Now you can see that alpha particles entering outside the inner circle, that is, through this annular ring, which I can mark, will come out through this zone. In other words, each pair of arcs marks out a zone of emergence that is directly related to each pair of circles in the approach area. Particles going in through this annular ring will come out through here, and particles going in through this largest annular ring, which I will mark, come out here. So now we're able to tell exactly where the alpha particles go. That is, at what angles they emerge. And in fact, we can also predict the quantities. For the quantities going in through each circular area are exactly the same quantities that come out through the corresponding zone on our sphere. Now let's think about the experiment. To take counts in an actual experiment of this type, we have to have a detector. And on this scale, the detector will be way out there. For you remember that this model just represents the minute core or nucleus of the atom and a little of the atomic space about the nucleus. For the purposes of argument, let's assume that all the particles that come out through this square on the spherical surface will hit our detector. And that's true not only at this position, but at any angle on the sphere. So our detector always sees a fixed fraction of the total spherical space about the atom. Can we arrange it so that our detector also sees a fixed fraction of the alpha particles coming through each zone? We can do it by choosing the areas of the zones to be equal. How do we do that? We do it by selecting the trajectories which divide up the zones. In our particular case, we wanted 4 zones, so we chose 4 trajectories that would make the zones have equal areas. This means that our detector always sees a fixed fraction of the alpha particles coming out through each zone. So if the number of alpha particles emerging from one zone differs from the number of particles emerging through another zone, the fractions striking our detector have the same ratio. So we have a uniform rain of alpha particles passing through concentric circles of various sizes, but emerging through spherical zones of equal size. Now look at this. All the particles which go in through this inner circle emerge through this cap zone, and those that go in through this outer ring emerge through this 4th zone, and you can readily see that the number of particles that will go in through this outer ring is much larger than the number of particles that will go in through this small inner circle. So the number of particles emerging through this 4th zone and going out to the detector will be much larger than the number of particles that goes out through this cap zone and into the detector when it is out here. So the key to our problem is the relative size of those input areas. With a uniform rain of alpha particles, the number entering the inner circle or any of the annular rings is going to be directly proportional to the area of that circle or ring. So now we can write that the number, capital N, striking our detector is proportional to the input area, A sub I. Now let's prepare a graph of the way we expect the data to appear. We will let the vertical axis represent the predicted number of counts. And the horizontal axis will represent angle, and will extend from 180 degrees to 0 degrees. We will let the number of particles that goes in through the inner circle and comes out through the cap zone into the detector be our unit number. And the cap zone extends from 180 degrees to 125 degrees. So on our graph, that portion looks like this, 180 degrees to 125 degrees at unit number. Now the first annular ring is 1.8 times as large as the inner circle. So 1.8 times as many alpha particles will pass through it and out through the first zone as went in through the inner circle and come out through the cap zone. That zone extends from 125 degrees to 98 degrees, and the count is 1.8. So that portion of our graph will look like this. The second annular ring is 3.7 times as large as the inner circle, so 3.7 times as many alpha particles will pass through it and out through its corresponding zone. This is 3.7 here. And the angular extent of that zone runs from 98 degrees to 74 degrees. So this portion of our graph will look like this. Finally, the outer annular ring is 15 times as large as the inner circle. Therefore, 15 times as many particles will pass through it and out through its corresponding zone as pass through the inner circle. 15 is up here, and the angular region of that zone is from 74 degrees to 45 degrees. So that portion of our graph will look like this. And now the character of the scattering pattern becomes apparent. You can see that far fewer alpha particles are scattered through large angles than are scattered through small angles. Now we have taken this calculation in large angular steps. If we had more time, we could have taken smaller steps and more of them, and we would have had a curve that looks something like this. You can see that the number of alpha particles varies continuously with angle, instead of being averaged over large angular intervals. Now there's a great deal of approach area out here in the atom, much more than the area we've considered near the nucleus. So most of the alpha particles in the rain hitting the atom go almost straight ahead, as Geiger had first seen. Those alpha particles that are only deflected by a degree or two would be plotted here on our graph, and there would be a great number of them. This part of the graph shows you the kind of scattering pattern Rutherford expected Geiger and Marsden to find at the larger angles. Here we have a carefully prepared graph based on his calculations. As before, the predicted count is plotted on the vertical axis, and the angle of the detector is plotted on the horizontal axis. Here, by contrast, we have a graph derived in a similar way for hard sphere scattering. And here is the curve you would expect if the deflecting force were proportional to 1 over r cubed instead of 1 over r squared, as in the Coulomb force. You can see that the three curves are different. Each curve provides a signature or fingerprint of the type of force that is at work in the collision. By February of 1911, Rutherford had prepared the curves for the electrostatic case. Within a few weeks, he had completed for publication a description of his nuclear atom model with the prediction that the scattering force was electrostatic. Then he set Geiger and Marsden to work at an experimental confirmation, which we could approximate with our apparatus. For each angular setting of the detector, the rate at which alpha particles struck the detector was carefully recorded. Work which took them months, we can do today in hours with our modern accelerators. After 18 months of painstaking effort, the scattering pattern Rutherford had calculated was decisively confirmed. Geiger and Marston's counting rates, plotted against their counting angles, fitted the curve characteristic of the 1 over r squared Coulomb force. Their data did not fit the curve for hard sphere collisions, and it didn't fit the 1 over r cubed curve. To be even more certain, they did experiments with foils of metals other than gold, and with alpha particles of different energies. And they all fitted with the prediction of a 1 over r squared Coulomb force field within the atom. Rutherford's extraordinary piece of deductive reasoning had given the world an entirely new concept of the structure of the atom. For the first time, it was seen as a sort of a minute solar system, with the nucleus as sun, carrying virtually all the mass of the entire system, with the bulk of the volume being empty space, permeated by intense electrical fields, and with the electrons distributed in this space, balancing by their negative charge the positive charge of the nucleus. Did Rutherford come to any conclusion about how small the nucleus actually was? He did. For even the alpha particles which approached the nucleus most directly scattered as he predicted they would, under the influence of a pure Coulomb force. And his calculations showed that the distance of nearest approach was less than 10 to the minus 11th centimeters. In an atom, which is 10 to the minus 8 centimeters in diameter, this charged massive core must be concentrated in a space which is smaller than 10 to the minus 11th centimeters. We can hardly see that on this scale. Let me give you an idea of the amazing image this creates. Let us suppose this point of light, 1 millimeter in diameter, to represent an atomic nucleus. I'm going to place it here. And then I'm going to ask you to back away from it. Further. Further still. There. From there, you should be able to see the whole of this circle. It's 3,000 millimeters in diameter. And on the scale of this model, it represents the outer dimensions of the atom. Now I'm going to take another point of light, also 1 millimeter in diameter, and let it represent a helium nucleus, an alpha particle. Is it any wonder that most of the alpha particles travel through the gold foil as though it were empty space? But it's a peculiar kind of empty space. Its outer dimension is as unassailable as the Greeks said it was. With all this space, why doesn't matter collapse? Why don't the charged particles of the other atoms move into this space? Another 20 years passed before that question was answered. That answer, and everything else we know about the atom today, are firmly built on Rutherford's triumph with its brilliant analysis of the force, mass, space relationship of the atom.
With this apparatus, you will be able to see what happens to electrons when they are acted on by electrical forces and magnetic forces that we can produce and measure. One of the things that we'll be able to determine from our observations is the mass of an electron. This tube contains a little hydrogen, and over here there's an electron gun aimed upward. The source of electrons is a heated cathode at the bottom of the gun. The electrons are accelerated upward by a potential difference applied between the cathode and the cone-shaped anode above it. The accelerating potential we read on this meter. Now, once we have a moving stream of electrons, we have a second way of controlling their motion, namely by a magnetic field. We know that a charge moving across a magnetic field has a deflecting force on it. We use these coils to produce our magnetic field. A current flowing around a circular coil like this produces a magnetic field at the center that has a direction perpendicular to the face of the coil and a magnitude proportional to the current flowing. This apparatus has two coils arranged in such a way that there is a very uniform electron is found within the tube. The effect of the field will be the same. Coils arranged in this way, these are one coil radius apart, are known as Helmholtz coils. You can see that the electrons are going to be moving upward in this direction. The field is horizontal in this direction, or perpendicular to the motion of the electrons. To measure the field strength, we read the current in the coils on this meter. I've made a calibration curve showing the magnitude of the field for each value of the current. As you might expect, it's a straight line. In other words, the field is proportional to the current. Now let's turn on the tube. We'll start with no magnetic field, that is, with no current in the coils. As I turn up the gun voltage, which you can read on the top meter, we see the beam of moving electrons. It's visible, or at least visible in the dark, because the electrons make the gas in the tube glow along the path of the stream. Now notice that since we know the voltage applied to the gun, we know the kinetic energy of the electrons as they leave the gun. The energy of an electron as it leaves the gun is equal to the energy per elementary charge times the charge. We have 100 volts on the electron gun, and each volt is worth this many joules per elementary charge. And now an electron has one elementary charge, so our Q is 1. And this is the energy of one electron as it leaves the gun. Now let's turn on the magnetic field, which will change the direction of the electrons, but of course won't change this kinetic energy. This time, watch the ammeter at the bottom. As we increase the field, we increase the deflecting force on the beam. Remember, the magnetic field is perpendicular to the path of the electrons everywhere on the path. Thus, the magnetic force is the centripetal force acting on the electrons. This force that keeps the electrons moving in a circular path of radius r is equal to the field times the charge times the velocity of the moving electrons. Since V occurs on both sides of this equation, we can write this more simply in terms of momentum. And we have quantities now that we can measure. We can measure B, the field, by reading the current and using our calibration curve. The current in the coils is 0.79 amperes. That gives, for the field, 0.97 times 10 to the minus 22. So we have this for the field, and Q is still 1. And now we have to measure R. Now, of course, we can't put a ruler inside the tube and measure R directly, so we have to use some kind of trick. There are a number of ways we could do this, but what I've done is this. I've taken a picture of the circle formed by the electron beam. Then I've removed the tube, and I've taken another picture of a scale put in exactly the same plane occupied by the beam. Here are the pictures. I've cut this along the scale, and now I can use it to find the diameter of the electron beam. The diameter is 11 centimeters, and R is half of this, 5.5 centimeters, or 0.055 meters. So here we have the momentum of an electron traveling in the particular circle that we've been watching. Now it's clear that from these two equations we can determine both the mass and the velocity. And when we do this, for the particular values we have here, we get the mass of an electron is equal to 0.89 times 10 to the minus 30 kilograms. Incidentally, the velocity in this case is about 6 times 10 to the 6th meters per second. Now I have the results of some other measurements that we've made with different values of V and B. Here you can see that although the accelerating potential varies quite a bit and the field varies, giving different values for the radius of the circle and for the velocity of the electrons, still, the value that we get for M turns out to be always just about 10 to the minus 30. In other words, no matter how we do this experiment, we always get about the same value for the mass of an electron. We can also check very easily how the radius of the electron beam depends on the voltage and current. You can see that by increasing the voltage, and thus the energy of the electrons, we make the circle larger. Increasing the field makes it smaller. In fact, if you want to do a little algebra, you can find out from these two equations exactly how R should vary with V and B. Finally, let's do one more thing. So far, we've been shooting the electrons straight up, perpendicular to the field. What would happen if we were to shoot them at an angle so that there would be a component of their velocity parallel to the field as well as one perpendicular? I'll rotate the tube like this, so that the direction in which the gun is aimed will make different angles with the direction of the field. The vertical component of the electron velocity will still be affected by the magnetic field, but not the horizontal component. Here, the gun's direction is at right angles to the field. As I change the angle, the electrons continue to circle around the direction of the magnetic field, but also move along the direction of the field until they hit the glass. I think you could predict the shape of this helix. All you need to know is the field, the gun voltage, and the angle of the gun.